Okay, in this video we're going to talk about a concept called line spectra. The idea on this is that basically when you have any given element or a molecule, the atoms can absorb and release energy in the form of light, but it turns out that they do it at very, very specific frequencies. Okay, so this is the broad topic of line spectrum. But before we get too far in that, we need to talk about something called a continuous spectrum. I guess I probably should point out, I'm not going to make a huge deal out of this, and I honestly screw it up a lot. Spectrum is singular, spectra is plural. So if you have more than one, the word is spectra. If you only have one, it's spectrum. Okay. So if you have a source of white light, white is made up of every color in the rainbow. It's all the colors at the same time. I'm literally going to draw it like an old school light bulb because I don't know what else to draw here. Okay. Light shining out in all directions, whatever. Okay. The light, as it goes this way, could in theory hit a prism. And as it hits this prism, it kind of bends the light, and the stuff that has the highest energy, the purple color, bends the most. And then as it leaves, it keeps bending. And so what we end up with is the Roy G. Biv thing. Okay? The idea, though, is that basically we are taking what your eyes perceive as white, like this paper in the background is white, and we are breaking it apart into the components that build up that white color. True white light should have an even balance, an even amount of each of these colors. Most white light that you see is close, like this LED light bulb that I'm using to light my thing. It's not perfectly white, but it's close enough that your eyes just kind of tolerate it. Okay, but if we had truly white light, you would get an equal amount of each of these. This is a continuous spectrum. Okay, you would get an equal amount of everything, and there would be no gaps in there at all. Spectrum. Okay. What we are talking about is something called a line spectrum, or line spectra in general. Okay, so the idea is that if you hit an atom with a source of energy, like light or heat or some sort of chemical reaction, whatever, okay, it can emit light, okay, but it doesn't emit a continuous spectrum. Okay, so if an element, doesn't have to be an element, but we're going to stick to elements right now. If an element is heated, or in other ways excited, basically if you hit it with light, if you have some sort of chemical reaction that occurs, it will emit light of very specific frequencies. Okay, and the idea is, of course, that basically the frequencies that it emits are very, very specific to that element. Okay, it can be used to identify elements. This is actually how they identify how old stars are. Brand new stars are pretty much all hydrogen, and hydrogen has a very specific line spectrum. Okay, as the star gets older, it starts making heavier elements like helium and lithium and beryllium, working its way down the periodic table. And the stronger those other lines are compared to the hydrogen lines, the older the star is. Okay, an example of a line spectrum. Again, I'm going to look at the textbook that I'm using. This is not any real specific textbook, I guess, just whatever I happen to have laying around. These are in terms of wavelengths here. So this is the visible spectrum like we're used to seeing it, like we saw in that part of the electromagnetic spectrum in the last video. So if you have hydrogen, we have 1, 2, 3, 4, and honestly, on a good day, in a real setting, you can sometimes see a fifth line. Okay, but if you have something like neon, you get a bunch of colors, especially in the orangish red, yellow region. you guys have probably seen this before. If you've ever been to a mom and pop restaurant and it has an open sign, it probably has a neon sign. It's literally just neon with electricity passing through it to get it to emit light. Okay, and it doesn't emit all the colors evenly, which is why it does not appear white. You're getting very specific frequencies that correspond only to neon. And your eyes just kind of blend them together the best that it can. And since most of the colors are in the yellow to red region, your eye sees it as orange. Okay. Hydrogen kind of comes off as like a bluish purple color, because most of them are in the purple and blues, and then there's a one red line. But your eye, there's 3 of those and only 1 of these here, but eye just kind of perceives it as kind of purplish. Okay? But the idea is that every element has its own unique line spectrum. Okay? Its own specific, very, very specific frequencies that it will absorb or release. So this is one way to see a line spectrum. The other is something called, so this is an emission spectrum. It's emitting it. Okay, so this is an emission spectrum. There's also something called an absorption spectrum. If you shine white light onto a pure element, it will absorb exactly those same frequencies, and what you'll get is a rainbow with those colors missing. Okay? It's like the opposite of an emission spectrum. So basically, atoms also absorb specific frequencies. So basically, if white light is shown on it, so all the colors possible, if a continuous spectrum is shown onto an atom, the line spectrum will appear as black lines in the rainbow. Oops, sorry, having trouble writing apparently. The line spectrum will appear as black lines in a rainbow. Black lines in the continuous spectrum. Okay, sorry, my handwriting got really messy there. Sorry about that. So, how do we know this? How do we figure this out? How does this work? Okay, well, there was this guy named Maxwell Planck. We're probably going to figure out in this chapter that almost everybody we're going to talk about has won the Nobel Prize somewhere. They're almost all dead now. Probably all are. Okay, so this guy, Maxwell Planck, came up with this idea that light doesn't travel. It travels as little packets of energy. Okay, and he referred to those as photons. So photons are packets of light energy. Okay, so basically light, when it's emitted, it's like when this light bulb's shining on things. Okay, it's emitting it in little packets of energy. Okay. And those packets of energy correspond to the various different frequencies. So if you have a white light, it's emitting lots of different frequencies and lots of different ranges of photons, okay? With line spectrum, you're only getting very specific energy options available, okay? So, he discovered this. It's Planck's quantum hypothesis. Doesn't really matter, honestly. I'm gonna write the word Planck. He was a German physicist, and he has an entire institute of physics named after him, like Science Institute, like his own university named after him in Germany, the Max Planck Institute of Science. Pretty ridiculously famous guy. Anyway, but he also came up with this equation that correlates energy and frequency. Okay, so this is the energy of the light, in joules, same units we saw in the last chapter. And this is the frequency, which we already saw in the last video, inverse seconds. And h is something called Planck's constant. I guess I'll label it over here just so I have space. Why they couldn't have used a letter that was in his name, I don't know. H is what they used. Okay. And the value is 6.626 times 10 to the negative 34th joule seconds. Just some physical constant of the universe, I guess. Partly based on the fact that we set seconds to be a certain interval of time. But anyway, so the idea though is the higher the energy, the higher the frequency, the higher the energy. This makes sense. If you think about, like, if you have a cliff and you have waves hitting it, the erosion factor, how much rock is being eroded away, has to do with how frequently it's being hit. The more it's being hit, the more frequently the waves are hitting it, the more likely it is to do erosion, the more likely it is to transfer energy to that wall. The same thing is true of light. So what's happening is if you have an X-ray versus a microwave, microwaves have a very, very long wavelength and a very long frequency. So when you get hit by it, you're not getting hit by all that much energy because it's not oscillating all that quickly. Whereas a X-ray is oscillating so quickly that every time it hits, it's going to do a lot of damage. Okay? But this guy was able to put some measurements behind it. Okay? So we'll stop there for right now.